Okay, so the formal definition of a power series about x equals a is this crazy looking thing with all these constants and exponents, but it's an infinite sum. Okay, you can think of this infinite sum as a polynomial with an infinite number of terms. Right? So it's just a polynomial where you have power of 1, power of 2, power of 3, and it just keeps going on and on and on. It's a polynomial of infinite degree. Or you can think of it as a function, so that if you plug a value in for x, each of these terms just becomes a number, and it becomes an infinite series, right? Where we just, which is what we've been studying for the past several days, how to add up an infinite series. So it's like infinite series, except it's got a variable in it now, instead of just strictly numbers. Okay, in the class after next one, we're going to use power series to approximate some complicated functions. But for now, we're just going to try to get through some of the basics of these things so that they become more comfortable. All right, so let's look at this power series. 1 plus x over 5 plus x squared over 25 plus x cubed over 125 plus x to the 4th over 625. What kind of series is this? It's geometric, yeah. What's the multiplier? The denominator is being multiplied by 5. What's the numerator being multiplied by? X, yeah. So this is a geometric series. And my multiplier, we'll call it R now because there's already x's in there. So my multiplier, which is, we'll just call it the multiplier, x over 5. All right, so if I wanted to write this thing in sigma notation, another word for that is closed form, I would write the sum from n equals 1 to infinity. And then what would I do? Need a formula for a general term. It's always going to be x to the something over 5 to the something, right? These are always x over 5s, and then we just have to raise it to a power. Right? So what power do I want to raise it to? N is a good option. If I make it at n, right, then when I plug in a 1 in here, my first term would be x over 5. But what's my first term? 1. X over 5 is my second term. How do I compensate for that? I could either do n minus 1 there, or I could start my index at 0. Either way. So now when I plug in n equals 0, I get 1. When I plug in n equals 1, I get x over 5. Plug in n equals 2, and I get x squared over 25. So that's this is the closed form of that sum, sigma notation. All right, so now I want to plug in values of x into this power series. Okay? So if I replace all the x's in this series with a 0, I'll write it in closed form first, and then I'll write out a few terms. So if I replace the x with a 0, this is the sum from n equals 0 to infinity of 0 over 5 to the n. Right? And what would that sum be? Why, when you plug in n equals 0, you get 0 to the 0. What is 0 to the 0? 0 to the 0 is undefined. Yeah. Because we have two conflicting rules here. 0 to the anything, 0 to, say, the 5th, right? 0 to the anything is 0. But anything to the 0 is 1. So you've got two conflicting rules there. And whenever that happens in math, we say like, oh my God, that can't happen. Yeah. So we say it's undefined. It's in there. It's the rest of the. So this is a little weird. This is something undefined, and then all the rest of the terms are zeros. Right. All right, if I plug in an x equals 1, then this becomes the sum from n equals 0 to infinity of 1/5 to the n, which would be 1 plus a fifth plus a 25th plus 1/125th, which is just an infinite series, and we know how to deal with that. It's a geometric infinite series. We know it converges because the multiplier is smaller than 1, and we know what it converges to. What does it converge to? Do you need a calculator? It converges to a over 1 minus x, right? Or 1 minus r, since we already have x's floating around here. R is the common ratio, or the constant multiplier. So my first term is 1. My constant multiplier is 1/5. So 1 over 4/5 is 5/4. All right, so you can think of this thing like a function, right? This power series, you can think of it as a function. You plug in a value for x, and you just get a geometric series. We know how to deal with those. All right, so let's look at what happens if we plug in x equals -3. So we've got the sum n equals 0 to infinity of -3 over 5 to the n. So if I start plugging in some values for n, I get 1. When I plug in a 0. When I plug in a 1, I get -3/5. When I plug in a 2, I get plus 9/25. And when I plug in a 3, I get minus 27 over 125. All right, does that series converge? Yep, the signs are alternating, the terms are approaching 0. Yeah, it converges. And it's also geometric, right? We can say if this is geometric and the constant multiplier is 3/5. So we could even figure out what it converges to. Actually, it's -3/5. But yeah, -3/5. All right, so let's see. What if I plug in an x though? I mean an x equals 6. N equals 0 to infinity of 6/5 to the n. I get 1 plus 6/5 plus 36 over 25 plus 6 cubed, 216. It's 216. Does that series converge? Yeah, the terms are getting bigger. Yeah, if you multiply by something bigger than 1, we're multiplying by 6/5 every time. So this is geometric, but to get from one term to the next, I'm multiplying by a number bigger than 1, 6/5. So those terms are getting bigger and bigger and bigger, and there's no chance of convergence. That's the test for divergence. The terms don't go to 0, it definitely diverges. All right, one more, -5. Didn't really leave myself enough room here. So this would be the sum, n equals 0 to infinity of -5 over 5 to the n. So it's -1 to the n. So this is going to be 1 minus 1 plus 1 minus 1 plus 1 minus 1. Does that converge? The terms don't approach 0. Yeah. Test for divergence says it does not converge. And you might be tempted to say that that goes to 0 because the 1s and the -1s will always cancel, right? But the partial sums is what, the sequence of partial sums is what we use to determine convergence. And my sequence of partial sums is going to be 1, 0, 1, 0, 1, 0. And that sequence does not have a limit, doesn't converge. All right, so what values of x will make this thing converge? I've done 0, 1, -3, 6, and -5. And this one, we'll say this one converges. Yeah. Yeah, because if you look at it in this written out form, it would be fine. It would just be 1, right? Yeah. Yeah, so maybe we just have to define this. I'll just say that my first term is 1, and then the rest, this is 1 plus the sum of 0 over 5 to the n, and we'll start at n equals 1 instead of 0. So that works. All right, so that one converges. This one converges, and we even found what it converges to. This one converges. It's geometric, alternating series, terms go to 0. This one diverged, right, because the terms were getting bigger. And this one diverges because the terms don't go to 0. So what kinds of x's can I plug in there to make this thing converge that will result in a convergent series? Yeah. The absolute value of x has to be less than 5. Because this is a geometric series, right? My constant multiplier is x over 5, and I need x over 5. The constant multiplier has to be less than 1, right? So I'll say because my ratio, my constant ratio, is x over 5 has to be less than 1 to get convergence in a geometric series, right? And then you just solve this thing for x, and so x has to be less than 5. So this answer, this absolute value of x is less than 5, this is like the domain of the power series. These are the only x's you can plug in that will give you a convergent series. Okay. And it's also called the interval of convergence. So if the absolute value of x is less than 5, what does that mean more specifically if I wanted to get rid of the absolute values? Be more explicit about what numbers I can plug in. Yeah, say louder. -5 to 5. So that's an interval, right? Or I could write it in interval notation, -5 to 5, right? So that's an interval of x values that will make that series converge. It's called the interval of convergence. All right, so we're going to look at a little animation file to see what the partial sums of this thing looks like. Because each partial sum of f of x is a function, right? So I just want to see what those partial sums look like. Record this. And then my fourth partial sum, which should be a cubic. And then I've got a quartic and a quintic. And I'm going higher and higher degrees here. Oops, hide that. Okay. So you can see that in this interval, -5 to 5, these are starting to converge to something. We've got a shape that these guys are approaching. And it turns out that what they're approaching is this function, 1 over 1 minus x over 5. That's the formula for a geometric sum. And that's the function. So this will converge to 1 over 1 minus x over 5, which would be, we'll just leave it like that, that's fine, when the absolute value of x is less than 5. Okay, so in the interval of convergence, that is what that infinite sum adds up to. Okay, so it's an infinite polynomial that converges to this rational function. All right, so let's look at another one. Here I have x minus 2 minus x minus 2 squared over 4 plus x minus 2 cubed over 9 minus x minus 2 to the 4th over 16. I want to write this in closed form. So that's summation notation. So these all look like, if I wrote this as over 1, right? My denominators are squares. So my denominators are all something squared. So I'll just put n squared under there. And my numerators are all x minus 2 to a power. And the power is the same as the number that's squared on the bottom. So we'll have that be n, and we'll have n start at 1. And you can always check if your formula is right by plugging in some n's, right? If I plug in n equals 1, I get x minus 2 over 1. And then if I plug in a 2, I get x minus 2 squared over 4, but it's positive. How do I make these signs alternate like that? I gotta have a minus 1 somewhere. To make the signs alternate, I could put in a minus 1 and raise it to, if I just did the nth, then my first term would be negative. So maybe I'll do like n plus 1. So my first term, I'll be squaring that thing and it'll come out positive. My second term, I'll be cubing it, and so it'll come out negative. Does that make sense? Okay. Okay, so I'm going to use the ratio test on this one to determine the interval of convergence, because this one's not geometric, right? The last one I determined the interval of convergence because it was geometric. So I could figure out pretty easily what values of x would make it converge. This one is not geometric. I don't have a constant multiplier from term to term. So I'm going to use the ratio test instead to try to figure out what values of x will lead to an infinite series that converges. So remember, the ratio test says you have to take that limit, and what does the result tell us? That limit has to be what to get convergence? Less than 1, yeah. So this is the one that was like similar to a geometric series. If this is less than 1, then we get convergence. So I'm going to plug in an n plus 1 into my terms, and then an n, and then look at the ratio and take the limit. Okay, so I should have written it up here. This is my series. Negative 1 to the n times x minus 2, whoops, that was n plus 1, over n squared. Okay, so if I plug in an n plus 1 in there, because I'm taking an absolute value, that negative 1 to the n plus 1 is completely irrelevant. All that does is change the sign, so I can just ignore it. I'm just not even going to write it down, because I'm just going to take the absolute value in the end. So this says x minus 2 to the n plus 1 over n plus 1 squared, all over x minus 2 to the n all over n squared. So it's the n plus first term over the nth term. Okay, and I dropped the -1 piece of it because I'm going to take the absolute value of all that. The ratio test has absolute value bars. And when you take the absolute value of -1 to a power, you're always going to get +1. So I just dropped it. Makes everything look a little cleaner. All right, so now I'm just going to simplify this complicated fraction. By doing a flip and multiply. All right, what can I cancel right now? Those can't, the n squareds can't cancel, no. Because n plus 1 squared is actually n squared plus 2n plus 1. And you can't cancel things that are separated by addition, right? Only things that are separated by multiplication. Yeah. I have n plus 1 of these on top of x minus 2's, and I have n x minus 2's on the bottom. So n of these will cancel with n of these, leaving 1. Okay, so I have a single x minus 2 on top. This is all an absolute value. I have a single x minus 2. And then this is times n squared over n squared plus 2n plus 1. Now, the x minus 2 doesn't change with the value of n, right? N doesn't affect this. There's no n's in that term. So I can pull that outside of the limit. So this becomes the absolute value of x minus 2. Well, actually, maybe I won't do that. Because n is always positive, because n goes from 1 to infinity. So I already knew that this would already be positive. Yeah. But technically it is in absolute values. All right, what happens to the n squared over n squared plus 2n plus 1 as n goes to infinity? Goes to 1, yeah. It's a rational function. Degree of the numerator and denominator are the same, so the limit is the ratio of leading coefficients. So this equals the absolute value of x minus 2, is that limit, right? And I have to, in order to get convergence, that limit has to be less than 1. I have to force that to be less than 1. Okay, so to get convergence, I can only, that limit has to be less than 1. All right, so if x minus 2 in absolute value is less than 1, that means that x minus 2 itself is between 1 and -1. You drop the absolute values. Does that make sense? If we did it in an easier example with the 5. If the absolute value of x is less than 5, that means x has to be in this interval from -5 to 5. Okay, so then we solve this, add 2 to both sides, and we get x has to be between 3 and -1 plus 2 is 1. So that is my interval of convergence. Using the ratio test to get an interval of convergence is very common for power series. Okay. Now the endpoints, x equals 1 and x equals 3, you have to test those separately. You have to plug them into your formula and test them separately. Replace x with a 1, replace x with a 3, and determine if you get convergence or not. but we definitely have convergence in between. Because remember, the ratio test, if it equals 1, is inconclusive, right? So you have to check the endpoints with another test separately. Okay, so let's look at another little graphical thing. Okay, so here's the infinite series, this infinite power function, polynomial with infinite terms. I'm going to graph its partial sums, and I've highlighted this interval of convergence that we found from 1 to 3. So there is my first partial sum. It's just x minus 2. And then my second partial sum has an x minus 2 squared over 4, so it should be quadratic. And then I'm just going to keep adding terms. Oops, missed one. So you can see that on this interval of convergence, these are all really close to each other. It looks like they are converging to something, and they are converging to, oh, that's just another partial sum. And we don't know yet, but we'll find out. So it looks like they're converging to a specific function, but only in this interval. After that, they all go off and do their own thing. In both of the problems we've done so far, the interval of convergence is centered on A, okay? Centered on some number A. In this case, the interval from 1 to 3, right? Its center is 2, right? So we call this the center of the interval, right? And it's A. And we call the distance from A to an endpoint of the interval the radius of convergence. So this distance we call R, the radius of convergence. Okay, so R for R2 power series that we've done so far, the interval of convergence for this guy was -5 to 5, right? Which means that what is my radius of convergence? 5, because this is centered at 0, and its radius of convergence is 5. In this case, my interval was 1 to 3, which means my radius of convergence is 1. Centered at 2, radius of 1. All right, so there are 3 possibilities for a power series about x equals a, when the power series is centered at a. So the series might only converge when x equals a. There might be only a single value that makes your series converge, and in that case, the radius of convergence is 0. Okay, if there's only one single x value, then your interval has no distance, right? And the interval of convergence, we say, is just, right, the number a. That's the only thing that makes it converge. The series might converge for all real numbers. It might converge all the time, no matter what x you plug in. And in that case, the radius of convergence is infinite. And the interval of convergence is -infinity to infinity. And then the third possibility is what we've looked at so far. And in this case, it might be that R is finite but greater than 0. And in this case, the radius of convergence varies, right? Some number R. And the interval of convergence is going to be a minus R to a plus R. Okay. So you start at the center of A, go left R and go right R, and you get your interval of convergence. Okay. Keep in mind, the endpoints of your interval always need to be checked separately because the ratio test is inconclusive when the limit of the ratio of consecutive terms equals 1. So you're going to have to use a different test from the last few sections. All right, so now some for you to try. Write each power series in closed form, that's sigma notation, and find the interval of convergence and the radius of convergence. So since most people got this, and you get the interval of convergence is 0 to 2, right? Which means that the center is at 1 and the radius is 1. Okay. But you have to determine separately whether or not you should include 0 and 2 in the interval. It definitely converges between 0 and 2. Does it converge when x equals 0? And does it converge when x equals 2? So let's start with x equals 2. So that means I'm going to replace all my x's with 2's in this series. So I'm going to have 2 minus 1 minus 2 minus 1 squared over 2 plus 2 minus 1 cubed over 3 minus, okay. So when I simplify this, I get 1 minus a half plus a third. And the next thing I would get is minus a fourth plus a fifth. Does this series converge? It converges because it's alternating signs and the terms go to 0. This converges, right? So that I go back up to where I wrote my interval of convergence, and now I'm going to include the 2 because I know it converges at x equals 2 also. And then when I look at x equals 0, I get 0 minus 1 minus 0 minus 1 squared over 2 plus 0 minus 1 cubed over 3. Okay, so this becomes negative 1. And I have a subtraction sign here. And then this term comes out to positive a half. And then I have an addition sign. But I'm cubing negative 1. So that actually becomes negative 1/3. And then I have a subtraction sign. And when I raise that to the fourth, I get 1/4. And I have minus a fifth. Does this series converge? It doesn't. I could factor out a negative 1 and I'd have 1 plus a half plus a third. And that's the harmonic series, which we know diverges. So I'm going to leave the 2 as the 0 as not included in the interval. So this is going to be your final answer. Don't include the 0, include the 2. So after you do all the work to get 0 to 2, then you have to do 2 more things to figure out the endpoints.